Hello, everyone. Thank you for being here. I'm very happy to be back at PyCon Germany. And today I will tell you about space weather and how we applied AI to build an explainable early warning system. Before starting, a few words about me. I have a background in theoretical physics, and I work as a machine learning engineer and data scientist in a research institute in Italy, which is the National Institute of Geophysics and Volcanology, where we study volcanoes, earthquakes, but also the upper atmosphere, the environment in general, and space weather. I also love community, and actually that's why we are here today. I'm one of the organizers of the local chapter of PyData in Rome. So if you happen to be in Rome, feel free to join us. We are always very happy to meet new friends. And this year, I'm going to be on the road to deliver some talks around Python conferences around Europe. So that's the agenda for today. We will start with space weather. And I don't know if everyone is familiar with this term, if everyone ever heard about that. Possibly not. So auroras are possibly the most striking consequences of space weather. But that's definitely not all the story. And indeed, before diving into the machine learning architecture, I would like to set the stage. So first, space weather. Just like we have weather on Earth, we have weather in the space. And this is the physical state of the near-Earth environment as it is driven by the sun's activity. You know, the sun is a variable star. It has a cycle which on average lasts 11 years. So when the sun throws a tantrum, like a solar flare or solar wind, this interacts with the planetary magnetosphere. And these interactions can have significant impacts on satellite operations, communication, power systems, GNSS accuracy. And that brings us to GNSS, which is a collective name for different constellations, like the GPS from USA, Galileo for us Europeans, GLONASS in Russia, Beidou in China. There are also some regional navigational systems, but we are focused on the GNSS side. We use GNSS for like every day, for everything from maps to also timestamping financial transactions. And it works by calculating incredibly precise travel times of radio signals from satellites down to Earth. But those radio signals do not travel through a vacuum. They have to pass through the ionosphere, which is a layer of the upper atmosphere extending roughly from 60 kilometers up to 1,000 kilometers. And this is filled with partially ionized plasma. This region plays a crucial role in radio wave propagation as it bends and delays the radio signals, acting like a giant mirror up in the sky, allowing for beyond the horizon communications. So when this density fluctuates, you can get positioning errors. And that's why we should care about space weather. This infographic actually perfectly maps out the domino effect of a solar storm. So this is not just about pretty auroras, but a direct threat to everything from satellites in orbit down to power grids and navigation systems. And when insurance giants like Lloyd's or even the European Commission publish risk reports on this matter, you know that this is a systematic vulnerability. A study from ESA, the European Space Agency, estimated that a single extreme space weather event could cause around 15 billion euros in socioeconomic damages in Europe alone. And that's because our mother infrastructures rely a lot on space-based systems. And since obviously we can't turn off the sun, our only defense is anticipation. And a few words about large-scale traveling ionospheric disturbances, which are the main topic of this talk. This is an effect, a space weather effect of the upper atmosphere. Those are plasma density fluctuations that are rippling through the ionosphere, and they are usually associated with auroral and geomagnetic activity. Okay, and they have real-world consequences since they can disrupt high-frequency communications and also GNSS positioning and timing. So the physical chain of the mechanisms involved in the formation of LSTADs, it's actually clear from a phenomenological point of view. You have something starting at the sun in the form of coronal mass ejection, which propagates through the solar wind. Then you have injection of energy at the higher latitudes, which then propagate equatorward as waves. And then you detect LSTADs at ground. So how did we build an explainable machine learning model for that? Everything, as I said, starts at the sun. So we had to figure out how to devise this task from a machine learning perspective. And despite the clarity of the mechanisms that I told you, which are responsible for the formation and of TIDs, the real-time monitoring and prediction of this kind of phenomena remains highly complex. So we frame this problem as a multivariate time series binary classification, which is taking different classes of inputs as physical drivers. So we tell the model something about the status of the ionosphere, something about the geomagnetic state around the Earth, so how currents are flowing around the Earth, some proxies for the forcing from the sun, from above, and also we tell the model something about the state of the sun. So where is it as a stage in its solar cycle, the number of sunspots, and so on and so forth. And we trained this model based on a catalog of instances which were manually labeled by ionospheric scientists. This catalog consists of roughly 1,600 events spanning 9 years, so covering almost the entire solar cycle. And the output of the model is trying to predict if LSTAD is starting or not over the European sector in the next 3 hours. Let's take a step back now. And when you devise a machine learning model, in general, you have to pick one, either a simpler model or a more complex one. And in general, when you choose simpler models, they tend to be more interpretable, but usually they may lack some accuracy. On the other hand, if you choose more complex models, like complex deep neural networks, they can be for sure more accurate, but they for sure lose some interpretability. So in order to achieve both, we worked like that. Of course, we wrote everything in Python. We used CatBoost as a framework for gradient boosting over trees. I don't know if someone is familiar with CatBoost. I'll tell you a bit more in a moment. Then we used MLflow for tracking the experiments and Noctuna for hyperparameter optimization. And then on top of that, we used SHAP as a layer for explainability in order to peek into the decision-making process of the model and also debug it. So, a few words about CatBoost. I'm sorry there are no cats involved, but it stands for category and boosting. And as I told you, this is a gradient boosting framework on decision trees, which handles efficiently and in a very smart way categorical variables, missing values as well, And it also has a peculiar architecture, which is the symmetric trees or balanced trees architecture, which has some nice pros like an efficient implementation on CPU, reduced inference times, but also a natural form of regularization. It also integrates seamlessly with SHAP as a method for explainable AI. And it's also very easy to use with Optuna for automatic optimization of the hyperparameters. In general, the trade-off between precision and recall or sensitivity is a function of the end user, which has to adopt and use the model. Why so? Because the cost of false positives is generally very different from that of false negatives. So instead of just delivering one model, we devised what we call 3 operating modes. So you might go for the high precision mode when the false positives are more costly. So, for example, you don't want to issue frequent unnecessary alerts that could lead to alert fatigue or costly countermeasures. On the other hand, an high recall or high sensitivity mode might be preferable for you when false negatives are more costly. So, for example, you want to detect as many real events as possible, even at the cost of some false alarms. Because missing an event for you could disrupt some critical communications, for example. So for early warning systems or safety critical applications, you will prioritize high recall or high sensitivity. But for operational purposes, operational systems with also possibly costly countermeasures, you might aim for the high precision mode, just to avoid overreacting to benign space weather fluctuations. And when false positives and false negatives matter equally to you, you can just go for the balance mode, which is the one that maximizes the F1 score. A few words about SHAP. So we have given centrality to trustworthy AI methods. And this in order to go beyond the black box approaches, placing some emphasis on the interpretability and explainability of the model. And this framework comes from the cooperative game theory, okay, where the inputs of the model are conceived as players taking part into a cooperative game, which is the machine learning model, and the output of this model is essentially a prize. Okay, so the output of SHAP is how can we fairly distribute the prize, the model output, among the players taking part into the game. And as you can see, the finally output is decomposed into a reference value, this one, plus a bunch of real numbers, which are nothing else than the feature contributions for a specific sample. So this is a local explanation, okay, where the sign tells you whether a certain driver pushed the prediction up or down, and the magnitude of the Shapley value tells you how strongly that feature impacted the model output. So SHAP turns the prediction into an additive story. And essentially that waterfall plot is just the additive path from the baseline to the final prediction. So with this tool in hand, we can peek into the decision-making process of the model, and we can see how it reasons over time and which drivers are contributing to the decision-making process. And when you aggregate those instances over the entire set, you can also build a global explanation in the form of a feature importance, a ranking of features which matter the most on average for your model. And this is very nice because this allows you to make contact with the domain expertise. In this case, it was physics, but it can be everything that you like. So this is very useful in order to build trust in the model to drive user adoption, but also to debug your model. Because you can go with this kind of charts to your fellow colleagues or to domain experts and ask them, is the model taking the right path, or is it just taking the wrong shortcut and it's not learning the meaningful things? But before shipping any model to production, you should characterize it a bit more. And we should understand that we have to move beyond point predictions. And to this end, we modeled risk and uncertainty for this model as well. So we are currently serving near real-time forecasts for this model via the ESWA platform at INGV, which stands for Electronic Space Weather for Upper Atmosphere. But the reasoning works like that. In the real world, acting on forecasts as a price tag. Cost-sensitive decisions can be more naturally addressed within probabilistic forecasting lens. And just for example, posing an expensive drilling operation because of a false alarm is costly. Sure, but missing a severe ionospheric disturbance could mean losing a drone or compromising a critical communication. And this equation essentially just formalizes that business logic. So the expected risk is just the probability of an event times the cost of that event occurring. So given accurate estimates of the costs that are associated with false positives and false negatives, you can build a system that automatically triggers decisions according to user-defined risk levels. But before using this approach, we have to understand that standard machine learning models are poorly calibrated. Why so? Because 90% probability is rarely a true calibrated probability. And in order to make some safe decisions, point predictions are not enough. And if you look at this chart, we are essentially serving not just a single probability line, but also prediction intervals. And so to get some robust intervals, we need to look beyond the standard outputs. So it comes uncertainty. Uncertainty quantification can be broadly divided in two classes of approaches: intrinsic methods or extrinsic or post-hoc approaches, based on the fact that you do require some retraining of the underlying model or not. And to give you some examples of methods, you can think of Bayesian approach and quantile regression as methods for intrinsic uncertainty quantification, while on the other hand, good candidates for extrinsic methods are calibration and conformal prediction. And I will tell you something more about conformal prediction, which, as you might guess, it is a statistical framework for any machine learning, actually AI model, to turn point predictions into prediction sets or prediction intervals. This is a nice approach, also a quite recent one, because it is almost distribution-free, in the sense that you, in general, just require some exchangeability, which is a milder IID assumption between test and calibration data. I'll tell you in a moment what calibration data is. So essentially, you ask that the distribution stays the same between test and calibration sets under some permutations of the data points. And that's the recipe for conformal prediction for one experiment. You can use it for classification and regression, and it's quite easy to achieve. Those are the ingredients. You need a model that has to be already trained. After all, this is a post-hoc method, so you do not require an explicit retraining. You need an heuristic notion of uncertainty, which is a metric, a distance between the x and y's. an error rate or an empirical risk that you have to set, say 5% if you want to aim at the 95% confidence level. And you need a pinch of fresh and unseen data for calibration. So you need a separate set for your model, training, testing, validation, and calibration data. And those are the instructions. You define the nonconformity score as a disagreement between your inputs and the outputs. You then evaluate those S scores, which are numbers, on the calibration set. So you learn this quantile, Q hat, which is related to the error rate that you set at the beginning of the process. And with this Q hat, you move from the calibration set to the prediction phase. So you can form prediction sets, and this has the nice property in the sense that the probability of a new unseen point belonging to the conformal set is related to the error level that you set at the beginning. And you have mathematical guarantees about that. And that's the key difference. I'm sure I confused you a lot because it's a complex topic. So if you want to learn more about conformal prediction, you can listen to my talk from PyCon Germany 2025. And wrapping up, trustworthiness is not just extra polish for your model. It's very important. And if you want to ship models in production and have reliable operations, you have to quantify your uncertainty. It's very important. And possibly also try to reason in a cost-sensitive perspective. And the thing is also that explainable AI and uncertainty quantification answer different questions for your model. So the first one belongs to the uncertainty side. Conformal prediction for this case gives you intervals or sets, and so the model can express the ambiguity instead of just pretending to be certain. And the other question goes in the direction of explainability. So SHAP for this case helps you attributing prediction to the relevant physical drivers and also opens the door to the scientific interpretation. So what changes is that the output becomes something that you can inspect, that you can challenge, and it's also something that you can then adapt to the user context. And that is why uncertainty quantification and explainable AI have to be part of the workflow, and not just a decoration at the end. And that's pretty much what I have for today, so I'm open for questions.
Thank you for your talk. Here are some questions. You mentioned around 1,600 events over 8 years. That seems like too little data to confidently predict an event within the next 3 hours. How did you solve this issue?
Okay, it's not too little. It's how the nature works, because we have this kind of events with a fixed rate over time. So we can't really tell the sun, oh, please try to produce more LSTADs. The thing is that, of course, we try to work with colleagues to enlarge the data sets. Of course, it was not possible to go backwards in time because there were not enough instruments for ionospheric measurements. We tried to control the confidence of the model by looking at the prediction intervals in output. So when the model saw enough instances as a specific sample, it was providing estimates which were narrow enough. So in this case, we were okay with the fact that the model was confident enough. For sure, when you deploy this kind of models to production, you have to account for concept drift, covariance shifts, and so in that case, you ship your model to production and monitor the performances, and then take action if you have to take some actions.
Next question. How do you encode the time series data to predict with the CatBoost? How far do you look back? Also goes in line with the data points across time questions?
Yeah, for sure, gradient boosting framework cannot understand what time is. So you have to perform some feature engineering tricks to tell the model something about the time. So this was done in the form of moving averages, exponential moving averages, also lagged features, which we were deciding how far back in time to go by looking at correlations between features and the target of the model. So if I remember correctly, we go back in time, we take into account like no more than the previous 6 hours of data, something like that.
Next question. If I understood correctly, you work on prediction of LSTADs. What happens next? How the collection of this effect is working? Are you sharing the results with GNSS companies?
That's a very nice question. I didn't mention that this was part of a European project, Horizon Europe project, and between the stakeholders involved in this project, there was the German Federal Police, the Bundespolizei, because they have instruments like the high-frequency direction finding systems, which are affected by this kind of events. So the first phase for this project was just building a model which can tell them in advance if something is going to happen or not. We are also working towards the integration into the European Space Agency monitoring room for space weather.
Next question. Do you know about some work that is explaining the instability of a given forecast?
I'm not sure that I understood this question. Explaining the instability, because I can understand what instability is, but I'm not sure what do you mean by explaining the stability. I don't know if you are in this room, maybe you can clarify.
Maybe next you can
I'm sorry.
about. Next one. Can you imagine some of these methods to be used in demand forecasting in explaining the models and their either causal dependency on the future covers used?
Yeah, for sure you can use these approaches in demand forecasting as well, but as you correctly pointed out, it would be much better to also look at the integration of causal inference, because the problem with this kind of models is that they are just learning correlation, and you are not sure that they are picking causal effects. So better to have both.
Last one. I graduated in a similar topic and I had no chance but using MATLAB because it provides important functions. How comes you were able to use Python?
But it refers to using MATLAB because... I'm sorry for that you had to use MATLAB. I don't know to what kind of functions are you referring to? Are you in this room? Possibly. Oh.
Yeah, for geometry and carrier function calculation, so the distance, but I think it was a bit off topic than your topic.
I have to be honest, it was quite easy to work in Python these days. I don't know when you graduated, but it was definitely easy and a joy because you have the full ecosystem for AI models. That, if you are curious, we can discuss it also later.
Okay. I think that we have already answered all. Okay. Thank you very much for the talk.
Very much.